Hello, in this video, we're going to take a look at another example of the integral test. So we are looking at the series k equals 1 to infinity of 1 over k cubed. And this means the function we need to check the properties about is the function 1 over x cubed, or x to the negative 3. And the three questions are, is f of x continuous for x greater than or equal to 1? And yes, 1 over x cubed is only the undefined when x equals 0. But defined everywhere else. So that first property, that first question, is true. The second question is f of x positive for x greater than or equal to 1? And yes, for x greater than or equal to 1, x cubed is greater than or equal to 1. So 1 over something that's greater than or equal to 1 is at least greater than 0. As this, it was greater than or equal to 1, but it's also greater than or equal to 0. So if that is greater than 0, so is the reciprocal. Great. The function is positive. And then the last question is f of x decreasing. This is the one that takes some time. And we do this with the first derivative test. So first derivative test. We have the function that is x to the negative 3. That means its derivative is negative 3x to the negative 2. F prime of x equals 0, or sorry, has a critical point. When it's undefined or when it equals 0. The derivative is undefined at x equals 0. That is the only place it's undefined, and it is not 0. The derivative is not 0 anywhere. So the only thing we'd be looking at is switching between negative and positive. However, to reiterate, we only care about 1 to infinity. So we don't care about the negative numbers. However, for the positive numbers, say x equals 2 or x equals 1. F prime, we'll say 2. We'll take a test point. Equals negative 3, 2 to the negative 2, or negative 3 over 4. This is negative. And so all the points from 0 to infinity are negative. F prime of x is less than 0 for x greater than or equal to 1. So f of x is decreasing. That is what the first derivative test tells us. Increasing for x greater than or equal to 1. Yes, the first derivative test is met. The integral test says once we have those three properties, continuous, positive, and decreasing for the function, we then look at the integral. Which we've done this integral, but I'll write it out quickly. To look at this integral, we want to look at the limit as t goes to infinity of the integral from 1 to t of 1 over x cubed, which is also x to the negative third. The antiderivative of that would be negative 1/2 x to the negative 2. And we still need the limit. Going from 1 to t. So plugging in our values, we have the limit as t goes to infinity of negative 1/2 t to the negative 2 minus negative 1/2 1 to the negative 2. Negative 1/2 1 to the negative 2 is negative 1/2. The limit as t goes to infinity, t to the negative 2 is also 1 over t squared. That denominator is growing, so the fraction is getting closer and closer to 0. This limit is 0, meaning we have negative of a negative 1/2 or 1/2. So the integral from 1 to infinity, 1 over x cubed dx, converges to 1/2. Therefore, by the integral test, the series of 1 over n cubed from n equals 1 to infinity also converges. And reiterating our sentence of conclusion at the end, we have the series converges or diverges by the test because of the other reason. And recall a property from the first video. Just because the integral converges to 1/2, the series does not converge to 1/2. It will be close to 1/2, but it's not 1/2. So we cannot say anything at this point about what that series converges to. All we can say is because the integral converges, then we know the series converges. Now, when we first started working this problem, or the integral of the problem, I said we had done this integral before. We have. It has been worked in the improper integral section. We already had found that that integral converges to 1/2. And in that improper integral section, we actually got a property of integrals known as the p-series test for integrals. There's a reason that for integrals word is on the end. There is also a p-series test, which is the exact same test, but it works for series. So the p-series test for series says the p-series sum n equals 1 to infinity, 1 over n to the p, converges for the same properties as the integral. So it converges when p is greater than 1 and diverges when P is less than or equal to 1. Recall also from the first video of this section that the series 1 over n, which is the harmonic, diverges. We showed it diverges because of integral properties and the definition of series convergence, but it also diverges because of the p-series test. P, in this case, would equal 1, which is less than or equal to 1, and that is when the p-series test shows a series diverges. So, another property for why the harmonic series diverges is due to this p-series test. So now if we have any series that's 1 over n to some exponent, we can tell very quickly if it converges or diverges. We've just got to be careful as to what we're looking at. Look at these two series, very similar. We have 1 over n cubed and 1 over 3 to the n. This first one is a p-series with p equal to 3, which is greater than or greater than 1. So the series n equals 1 to infinity 1 over n cubed converges. Series converges by the test with the reason. The second one, because the 3 and the n are switched, this is actually geometric. This is actually the series n equals 1 to infinity of 1/3 to the n. So this is a geometric series test with r equal to 1/3 and a equal to 1/3 to the first, plug in the lower bound, a is also 1/3. So the series n equals 1 to infinity of 1 over 3 to the n converges by the geometric series test because the absolute value of r is 1/3, which is less than 1. And it converges to 1/3 over 1 minus 1/3, a over 1 minus r, which comes out to be 1/2. So we have the geometric series test and the p-series test can look very similar, but if we have an exponent of a power, that's going to be geometric. And or our variable is an exponent, it's going to be geometric. And if our variable is in a base in that denominator, it's going to be more than likely p-series. And now we have these two big tests that can help us tell convergence or divergence. In the next video, we'll get one more really big test for this section. And then look at one more thing we can tell with integral test properties.